Okay, let's now pursue a thermal example within the FEM capability in SolidWorks. So this is going to simulate a curling iron. This will be a very, very coarse, type of approximation, just enough to get a sense, for how we can set up one of these problems, and to where we can see the parallels between setting up these restraints and loads in the structural world to their equivalent in the thermal world. Okay, so let's take a tube in here that will approximate our curling iron, such as it is. So 2 inches in diameter, 6 inches long, and a 0.1 inch wall thickness. So this is just a hollow tube. We're going to ignore the effects at either end. And what we're going to do is impart a thermal load here at the entrance, here, or the inside of the tube, I should say. So let's imagine that we have a heater element built in there that's going to deliver uniformly 85 watts of power into the tube from the inside. And then we're going to set up the equivalent of the boundary conditions, for the thermal world, which will be a convective heat transfer between the surface, the outer surface of the simulated curling iron to the environment, with a particular value which is representative of a quiescent air type of condition. So just if you had a hot object sitting in still air, so it would convect heat to its environment at the rate of approximately, and there's a very rough number, but useful for our purposes. We're going to use a number of 20 watts per meter squared degree Kelvin or degree centigrade, either way. Okay. Right, so our access to this is, first of all, going to be the SolidWorks add-in of simulation. Okay, so first order of business is to turn that on after we have created our model. Okay, and then once in here, just click on the simulation tab here, and under the study advisor button. Now this will function similar to a wizard, but in this case I'm just going to pursue a new study. Now we're working here with a full strength version of simulation within SolidWorks. Okay, so as you do a new study in here, you'll see that you can do several different types of studies. So notice in a static, that would refer to the strength analysis, similar to what we did in a previous video lecture. Here's the thermal that I'm going to select. Frequency study, buckling, drop test, fatigue, pressure vessel design. You can see how extensive all these capabilities are within SolidWorks. So we're just going to just barely scratch the surface, but enough to know sort of what's available and what goodies are at our disposal. Okay? So I'll go ahead and click on thermal here. Click OK, and we are going to be, so again, instead of using a wizard, instead, we're just going to fill in the parameters here directly. So I already have a particular material assigned to this tube, 316 annealed stainless steel bar. Connections I will not need to worry about, since this is just a simple single part. Now for thermal loads, this is where I get to assign the different conditions that I described before as being thought of as loads or boundary conditions. So my first load is going to be a heat power load. I'm going to select SI as my system of units, which will give me access to watts there. And let's go ahead and put in the 85 watts that I was talking about. Okay, so that's I'm going to select this face, the inside face, as the recipient, if you will, of that power input into the system. And that's all we need to do. So we'll just hit OK here. The next thermal load that I'm going to select is the convective temperature, or rather the convective effect that's going to be experienced by the different faces. Okay, so here, let's see. Well, first of all, I'll select the faces. Select this, and in fact, we'll go ahead and select the end faces as well. So we have 3 faces in there, and again, the end conditions are not really realistic, but we'll just ignore them for purposes of this simulation. Okay, so I have 3 faces. I'll again select the SI system of units, and for my convection coefficient, I'll pick this 20 watts per meter squared degree Kelvin that I was talking about. This has to be done in reference to a bulk ambient temperature. So in this case, we'll say that we want the ambient temperature to be just room temperature, so approximated as 300 degrees Kelvin. Okay, that would be about 22, 23 degrees centigrade. Okay. All right, so with these conditions, we are, believe it or not, ready to go ahead and run a so-called steady state analysis. Okay, so to do this, we are going to access this tab here, run this study. Okay. Now, if we just say run this study, even though we have not yet created a mesh, this will be done automatically. Okay. So a mesh is created, then the study is run proper. And very rapidly, we obtain a result in here. We see the heat map, and we can now take a look at this chart. Fortunately, the defaults in here for the chart are not particularly useful in there, or friendly, I should say. They're in degrees Kelvin, and we have a strange convention in there, scientific, supposed to engineering notation. So let's go ahead and fix that. You can right-click on it, edit the definition, and change, for example, the display to be in degrees Fahrenheit. If we come here under chart options, we can also control things like whether the maximum and minimum annotations are shown, automatic versus defined, so we'll leave it in automatic on there. And we can also control the format of the numbers, which is often useful. In fact, this is changed to floating with a single significant digit, or rather a single decimal point, I should say. Okay. So now it's showing a range between 377 and 390 Fahrenheit. Okay, we can see that the maximum temperature occurs at the center of the tube, and this makes sense, for the very simplistic conditions that we have enforced, since there is some heat transfer occurring here at the very ends. Okay, but already this number it's not crazy. It's actually representative of what a curling iron, would experience under the roughly 100-watt condition that we have specified. And this is what we call a steady state condition. So this is not taking into account any transient behavior. In other words, after the 85 watts have been applied and the temperatures have stabilized and the system is operating at steady state. Now, interestingly enough, we can also do a transient analysis. It's very easy to set up. There are effectively a couple of simple steps to the transient analysis. So one thing that we would do is modify the nature of the study here. So if we go here to right click on thermal and go to properties, we see here that we're running a steady state simulation, but we can switch over to a transient simulation. Okay, let's say that we set up the simulation over the space of an hour. So 1 hour would give us a total time of 3,600 seconds. And here our time increment, this is very similar to the concept of the resolution of the frames per second in the motion study. So for the time increment, we'll do this once every, let's say every couple of minutes. So we'll do this at 120-second increments. Okay. Now we do need an initial temperature. This allows you to perform a study and then use the final temperatures of that study as the initial conditions, for a subsequent study. In this case, that's not what we want to do. We'll just specify a starting temperature. Okay. And that is available again under thermal loads here for temperature. Okay. And here we have the ability to set up an initial temperature. And we'll just select the body for initial temperature of, let's say, room temperature, which would be rather reasonable. Okay. Now in here, you have to pay attention to this. If you just click in there, you're actually just selecting a face. Okay. So don't do that. Instead, what you do is you invoke the filters. So I'll just type in filter here at the help menu. Let's turn on the filter toolbar and make sure that I am selecting solid bodies. Okay, so I can now select that body and know that I'm specifying the initial temperature for the body, not just for the outside faces, or the inside faces for that matter, but through the body. Okay? And again, I'll set up an initial temperature, just room temperature, so 300 Kelvin. So that's where our transient condition begins. We start with everything at room temperature, turn on the power, okay, the 85 watts, and then we're going to see how the temperature goes up. Okay. So we'll click OK. We can get rid of our selection filter, and we'll just go ahead and run the study. Okay. So we'll see that the study is progressing through 30 steps, spaced 2 minutes apart. And what it's doing is it's progressively calculating based on the inputs and the loading conditions, what the temperature development is within this body at each one of those steps. At the end, we're going to be able to select a point and then graph the temperature curve over time. That's an indication of the transient behavior of the curling iron. Okay, so let's see how we do. Will an hour be enough to reach steady state temperature? Will it come up to steady state temperature sooner? Well, let's find out. So here we are, just about done. Okay. First thing we notice, if we look at the graphing here, is we are at 140 some degrees Fahrenheit, which doesn't seem to make any sense until you realize that really just refers to the first step being 120 seconds into the study. Okay. So we can progress, through the different steps. Now, when you have a transient simulation here, not only do you have to worry about the results in the field, in the volume where they occur, but also across time. So there are multiple plotting tools that are available to represent the data that you seek. Okay. So the access for that is plot tools in here. And one of the things that you can do with one of the many things I should say that you can do with the plotting tools, which is useful to us specifically, is the probing. Okay. Even before we look at the probing, let's take a quick look at animate in here, and we'll just go ahead and run the animation as is. Just let it do its deed. Okay. And we can follow up here where we are in time, and you can see the maximum temperature jumping, and that's just an artifice of the precision of the simulation. Okay, but we can see here, if we take careful attention, that we seem to be reaching somewhere in the neighborhood of 400 C towards the end. Okay, there are means to control the simulation. We can put in more frames in there, do reciprocating, also being able to loop it, etc., just like we did with motion study. Okay. Well, the more interesting one for our purposes is going to be the probe tool. Now, for the probe tool, all I'm going to do is just going to select a particular node. I'm just going to pick it, just approximate it there in the middle. And it's not essential where exactly, since this, the difference in temperatures is going to be fairly minor in that area. Okay. And now I'm going to come here down to report options and select this one called response. So this will create a plot over time. Okay. So as we do that, so we're plotting that particular node over time, and it looks like try to get something to us. And there it is. A little shy. Okay, and here we have it. So we have a progression there from the first step, which takes place at time 120 seconds. Okay, so we would have started at room temperature, so say 77 Fahrenheit or so. Okay, we would have progressed to about 140 Fahrenheit in the first 2 minutes. And then we can see that as time passes, there we have a progression, and then we finally seem to reach steady state a little bit shy of 400 Fahrenheit at some point around here. Overall, shall we say about 40 minutes is the time that we would expect for this particular model of the curling iron to reach steady state temperature, to reach effectively the final value. Okay, so it's important to point out simulation is as powerful as it is dangerous. Okay, you need to. This is an art. This is a skill that you develop over a long period of time. It requires great thought. Great care. You can get beautiful plots out of complete nonsense, and you always have to have a very critical eye to make sure that you're modeling the effects that you're interested in, to make sure that you're not over modeling, and that the results make sense, so that that is the critical element in not just having a tool available that you can click here left and right, but also the knowledge of the underlying physics and even some of the underlying math algorithms that give you these results. So a lot of power, a lot of cool stuff that you can do with this, a lot of insights that you can receive, and I hope that you take advantage of it over time.